You know, it is kind of funny how our language really shapes our perception of technology. We use terms like uh, the cloud or wireless or virtual.
Right, yeah.
And we talk about artificial intelligence as if it is this, I don't know, this ethereal, glowing brain just floating somewhere in the ether.
It's very clean.
Exactly. When you type a prompt into an image generator or you ask a language model to analyze a spreadsheet for you, the interface is totally clean. It's silent. It gives this really strong illusion that data is just, well, weightless.
I mean, that is a brilliantly constructed illusion, right? Consumer technology is entirely designed to hide that mechanical reality from the user. We just want the magic trick.
We don't want the backstage view.
Exactly. No pulleys and levers for us. But the physical backstage, where the cloud actually lives, is just the furthest thing from weightless or silent.
Oh, not at all. If you actually walk into a modern hyperscale data center, I mean, that illusion just drops instantly. You aren't stepping into some quiet library of information.
No, you're stepping into an environment that is violently physical.
Violently, like it is loud enough to cause permanent hearing damage.
Yeah, and the airflow in those aisles is literally strong enough to lean against. The scale is difficult for most people to even comprehend.
It's heavy industry, plain and simple. The data center really is the factory floor of the 21st century, and the raw material that they're processing millions of times a second is just raw electricity.
Which generates a terrifying amount of heat.
Which perfectly brings us to why we are here today. So, welcome to the deep dive. Today, we are taking you on a journey into this incredibly loud, heavy, and hot reality of modern computing.
It's going to be a fun one.
We're going to decode this highly technical piece of source material. It acts as a sort of Rosetta Stone for understanding this physical world. We have this really comprehensive engineering data sheet from Supermicro.
Right, detailing their rear door heat exchanger product line.
Or, as the industry abbreviates it, the RDHX.
And I should say, for anyone just glancing at this document for the first time, it can be pretty intimidating.
Oh, it's dense.
It's a completely unvarnished engineering spec sheet. We're looking at thermal capacity limits, complex U-height matrices, AC versus DC power draw metrics.
Just a wall of numbers.
Yeah, variable fan topologies. It's just this dense wall of physical parameters.
That is exactly our mission for you today. We are going to translate all those raw parameters into a really clear, vivid picture of cutting-edge infrastructure.
Because hidden inside these, seemingly dry specifications is actually the solution to this massive invisible crisis in modern tech.
We're talking about the actual physical limits of thermodynamics and how hardware engineers are desperately trying to keep the internet and especially the booming world of generative AI and high-performance computing from literally melting down.
And that term melting down, it really isn't hyperbole. If you look at the thermal design power, the TDP of the newest generation of AI processors, the heat output is just staggering.
It's off the charts.
It really is. We are no longer dealing with hardware that can be managed by traditional means. The physical infrastructure of the internet is basically being forced into this radical evolution just to survive the heat its own chips are generating.
So let's start with the baseline of how things used to work, right? Because I think that really highlights why this Supermicro RDHX datasheet represents such a massive shift.
Yeah, context is important here.
For decades, the standard philosophy for cooling a data center was basically just room-level air conditioning on steroids.
Right. The industry term for that is CRA, computer room air conditioning.
Catchy.
Yeah, very. The concept is pretty straightforward, honestly. You build a massive warehouse, you fill it with rows of server cabinets, and then you just pump an astronomical volume of highly pressurized, freezing cold air into the room.
Usually under a raised floor, right?
Exactly, under a raised floor or through these massive overhead ducts. The servers pull that cold air in through their front panels, the air washes over the hot processors inside, and then it gets exhausted out the back as hot air.
So it's basically brute force thermodynamics. You are treating the entire building as this single thermal envelope.
Yep.
But as I was reading through the capabilities of these new RBHX units, it becomes pretty clear that the brute force method has hit a massive wall.
Oh, it absolutely has.
Because when an AI cluster is running, a massive training model, the heat isn't evenly distributed across the room. You get these really hyper-localized thermal blooms.
Right.
It just seems like trying to manage that by turning up the AC for the whole building would be profoundly wasteful.
Wasteful, and eventually it just becomes structurally impossible. Think about the inverse square law of airflow, and then just the sheer volume of space in a modern warehouse.
Massive.
Right, so if you have a single rack generating a massive thermal load, pumping cold air into the general vicinity means a huge percentage of that cooling energy is just wasted. You're
Well,
chilling the empty aisles, the ceiling space, racks that aren't even running hot.
right.
And worse, you run into what we call the bypass airflow problem.
Okay, wait, what exactly is bypass airflow?
So that's when the cold air being pumped into the room mixes with the ambient hot air before it even enters the server chassis.
Oh, I see.
Yeah, so by the time it reaches the actual processor, it's already lukewarm. It completely loses its thermal transfer efficiency.
So the Supermicro datasheet proposes this totally inverted philosophy. Instead of trying to freeze the whole room, they target the heat at the exact boundary layer where it exits the machine.
Right at the source.
They are essentially replacing the standard, metal back door of the server rack with this massive, highly intelligent, liquid-filled radiator.
Yeah, the datasheet repeatedly uses the term residual heat, and that really is the operational focus here.
Residual heat. Okay.
The RDHX intercepts that residual heat immediately after it leaves the server chassis.
Yeah.
Before that 100-degree air can disperse and just ruin the thermal profile of the wider room, it crashes into this massive array of liquid-cooled coils.
And those coils are built directly into the rear door. So the heat transfers into the liquid running through the door, and the air that finally passes out into the room is basically entirely neutralized.
Yep.
It's just room temperature again.
Which is precisely the goal. You are trapping the thermal energy at the source. And this is what enables what Supermicro calls maximum compute density.
Because space is money.
Exactly. Data center real estate is incredibly expensive. Operators want to pack as many GPUs into a single square foot as physically possible. But, density breeds heat.
Right.
By neutralizing the heat at the rear door, you completely isolate the rack from the rest of the room. You could theoretically place a rack generating massive heat right next to an older, much cooler rack, and they wouldn't cross-contaminate the room's overall temperature at all.
That's wild. And the cooling capacities listed in this document are kind of difficult to wrap your head around.
They are extreme.
They are dealing with heat removal ranging from 10 kilowatts for legacy systems, all the way up to 120 kilowatts for a single rack.
Yeah, so to ground that 120 kilowatt number in everyday reality for a second, consider a standard household space heater.
Okay, I have one under my desk.
Perfect. A powerful one of those pulls about 1,500 watts or 1.5 kilowatts. So neutralizing 120 kilowatts of thermal energy is the equivalent of taking 80 of those space heaters.
80?
80 of them.
Yeah.
Turning them all onto their maximum setting and cramming them into a space roughly the size of a kitchen refrigerator.
Wow. And the RDHX has to absorb every single joule of that energy.
Every single bit of it.
That is just an incredible engineering feat, just to visualize. But a door, even one filled with chilled liquid, is ultimately just a passive barrier unless you have a mechanism to force the air through those dense cooling coils. Right?
Absolutely. The coils create resistance. Engineers call that static pressure.
Okay.
The tiny server stands alone just can't push the air through that secondary barrier.
So that is where the active mechanical components come into play. The RDHX isn't just plumbing, it is this active aerodynamic system.
It really is.
The datasheet details this highly specific approach using multiple fan arrays to pull the air through the coils.
And this is where the engineering gets really interesting. They heavily market this N+1 redundant fan design combined with intelligent speed control.
Right.
Depending on the specific model we look at later, these doors integrate anywhere from 3 to 12 massive industrial fans.
And this N+1 redundancy, it seems like a non-negotiable requirement at this level of computing. I mean, it's a standard engineering framework, but the application here is fascinating given the stakes.
Oh, the stakes are incredibly high.
Yeah.
Let's unpack N+1 for the listener for a moment.
Yeah, please do.
In a mission-critical environment, N is the baseline. If the physics dictate that a door requires exactly 6 fans operating at full capacity to neutralize that 100 kilowatts of heat, then N equals 6.
Right, the bare minimum to do the job. And then the +1 provides the failsafe.
Exactly. So the system is designed with 7 fans total. But the real ingenuity isn't just having an extra fan sitting there, doing nothing until there's a problem. It is how the system dynamically manages failure.
This was my immediate question when reading the spec sheet. If you have a rack generating the equivalent of 80 space heaters and a fan motor suddenly burns out, Won't the servers inside overheat and crash in the minutes it takes someone to swap it out?
It's a very valid fear.
I mean, a dead fan creates a physical hole where air will just stall or even flow backward because of the pressure differential. A technician can't run down the aisle fast enough to fix it before the AI cluster melts.
You're touching on a really critical fluid dynamics problem there.
Yeah.
When a fan dies in a pressurized array, you lose the vacuum effect in that specific zone.
Right.
But this is where that intelligent speed control acts as the immediate failsafe. These motor controllers operate on millisecond latencies.
Milliseconds.
The absolute moment a fan registers a drop in RPM or a total power failure, the localized system doesn't wait for human intervention.
It just compensates instantly.
Instantly. Let's use a physical analogy. Imagine a heavy wagon being pulled by 4 horses.
Okay.
If one horse suddenly stumbles and drops out of the harness, the wagon is going to instantly decelerate, and the remaining 3 horses will be thrown off balance by the sudden shift in load.
Sure.
But imagine if, the absolute microsecond that one horse dropped, the other 3 instantly, perfectly increased their pulling force by exactly 33% to maintain the exact same speed and momentum.
So the wagon never even twitches.
Exactly.
In the case of the RDHX, the remaining fans dynamically spin up to a vastly higher RPM to compensate for the lost airflow. The static pressure is maintained, and the servers inside the rack don't experience even a momentary dip in cooling.
They remain completely oblivious to the hardware failure happening inches away from their exhaust ports.
That's amazing.
And this dynamic compensation is what enables the feature Supermicro calls hot swapping. Because the system stabilizes itself at a higher RPM, a data center technician can casually walk up to the rack, unlock the rear door, manually pull out the heavy, broken fan module, and just slot a replacement unit right in.
All while the AI models continue training at 100% capacity.
The system never goes offline.
So that is the zero downtime reliability promised in the datasheet. It is mechanical fault tolerance driven by digital intelligence.
Very well put.
But of course, driving 6 or 12 industrial fans at variable, extreme RPMs introduces a massive electrical demand, right?
It pulls a serious amount of power, yes.
Which opens up a whole new set of physical risks. We're talking about running high voltage power directly alongside high volume liquid cooling.
A classic combination.
Seriously. To anyone who has ever accidentally spilled coffee near a power outlet, the idea of intentionally putting a massive water loop millimeters away from the power supply of a multi-million-dollar server cluster seems inherently insane.
It definitely sounds like a recipe for disaster. It requires extreme mitigation strategies. Let's look at the power integration first, because how electricity is delivered to the doer really impacts the physical layout.
Right, which in turn impacts the airflow and the overall safety profile.
Exactly.
Well, the datasheet makes a point to highlight the power delivery for their DC direct current models. It states that they integrate seamlessly with the rack's shared power bus bar.
Right.
Now, for those who might just picture standard power cables plugging into a wall, a bus bar is a fundamentally different approach.
It completely eliminates the concept of individual power cords. A bus bar is essentially this thick, solid spine of conductive metal, usually copper or aluminum, that runs vertically down the back of the entire server rack.
Just a giant spine of electricity.
Yeah, and it carries a massive, unified, direct current payload.
So instead of hardwiring every single component, running individual cables to a massive power strip, you just physically clip the RDHX door directly into this electrified spine.
Clip it right in.
It draws its required wattage straight from the central bus bar, like snapping a battery into a power tool.
That's a great way to think about it. The datasheet notes that this streamlines deployment and significantly reduces installation time. But the hidden benefit, and the one that matters most to thermal engineers, is cable reduction.
Oh, interesting.
In a traditional rack, the rear exhaust area can look like a jungle of thick black power cables. Those cables create physical drag.
They get in the way of the air.
Exactly. They block the air from escaping the servers, creating turbulence and back pressure.
So by using a unified bus bar, you literally clear the physical airspace. The air can flow straight from the server exhaust into the cooling coils without hitting a wall of plastic cabling.
It enhances the aerodynamic efficiency of the entire rack.
That makes perfect sense.
But, as you pointed out earlier, optimizing the airflow and utilizing liquid cooling creates a much more terrifying physical threat than just heat.
Right. Moisture.
Water.
It creates moisture. The datasheet prominently features this smart anti-condensation system. Yeah, and when I read anti-condensation, it honestly felt like reading a contradiction. You are bringing extreme, rapid cooling into a hyperheated environment.
Right.
Basic physics dictates that condensation is going to occur. I mean, if you take a freezing cold can of soda outside on a humid summer day, it starts sweating immediately. The water vapor in the air condenses on the cold metal.
And that is the exact thermodynamic nightmare data center operators face. The psychrometrics of a server aisle are highly volatile. When that 120 kilowatt heat hits those chilled liquid coils, the metal of the coil acts exactly like your soda can.
But a sweating soda can just leaves a water ring on a picnic table. If a 120 kilowatt heat exchanger starts sweating, gravity is going to pull those water droplets straight down into the data connections, the bus bar, and the server motherboards.
It would be disastrous.
Right, a single micro drip could arc a connection and destroy a GPU cluster worth hundreds of thousands of dollars.
It would be an absolute catastrophe. So the anti-condensation system isn't just some nice-to-have feature. It is arguably the most critical safety mechanism in the entire unit.
It has to prevent the sweating entirely.
It has to constantly calculate and defeat the dew point.
But the dew point isn't a fixed number, right? It constantly fluctuates based on the ambient temperature and the relative humidity of the room. How does a mechanical door actively prevent physics from happening?
It requires a localized, real-time feedback loop. The RDHX is covered in environmental sensors that are continuously polling the ambient humidity and temperature of the air entering the coils.
Okay, constantly watching the air.
Yes, and a dedicated controller is running constant psychrometric calculations to determine the exact dew point in that specific square foot of the data center at that exact millisecond.
So if the ambient humidity suddenly spikes, say, because the main building HVAC shifted or someone opened a door, the dew point changes?
Instantly. And the door's mechanical response relies on a modulating valve controlling the flow of the chilled liquid.
Oh, I see.
The system is essentially walking this thermodynamic tightrope. It must keep the metal coils cold enough to neutralize 120 kilowatts of residual heat, but it must dynamically throttle the liquid flow so the metal never, ever drops below the real-time calculated dew point.
Wow. So it is actively blending or restricting the coolant to keep the surface temperature of the radiator just degrees above the danger zone.
Exactly. It is a localized climate control system making micro adjustments hundreds of times a minute.
Which brings up a huge logistical question for me. With the fans dynamically adjusting their RPMs for N+1 redundancy and these modulating valves constantly throttling liquid to fight off the dew point, how does a human being actually keep track of all this?
That's a lot of moving parts.
A hyperscale data center doesn't just have one of these doors. They have rows upon rows of them, thousands of intelligent doors making independent decisions.
That requires a multi-layered digital nervous system.
Yeah.
The datasheet breaks the management and monitoring down into physical and network-level interfaces.
And the most surprising inclusion for many people is that the RDHX features a built-in, localized touchscreen interface right on the chassis.
Yeah, I have to admit, that specific spec really gave me pause. A physical touchscreen feels incredibly out of place here.
It does seem weird at first.
We established that the hot aisle of a data center is a hostile environment. It's over 100 degrees, the ambient noise is deafening, and technicians are wearing heavy ear protection.
Not exactly a place you want to hang out.
Right. Why would anyone design a system that requires an operator to stand in that physical environment tapping on a small screen? Surely everything is routed to a centralized dashboard in a nice, quiet control room somewhere.
It seems counterintuitive until you factor in the physical maintenance realities we discussed earlier. The touchscreen is not designed for overarching daily monitoring.
Okay.
It is a highly tactical, boots-on-the-ground diagnostic tool.
Ah, for the hot swapping scenarios. Exactly. When a technician is dispatched to physical aisle 4, rack 12, to replace a failing fan, they are stepping right into the danger zone.
Right.
Before they physically unlock that door and expose the internal mechanics, they need absolute confirmation of the localized state. The touchscreen provides immediate, zero-latency readouts of the internal liquid pressure, the flow rate, the localized dew point calculations, and the operational status of the remaining fans.
So they need to verify that the N+1 redundancy has actually engaged and the pressure is stable before they start pulling hardware out.
Exactly.
It's basically an emergency dashboard right at the point of contact.
It provides physical confirmation in a physical environment. But you are entirely correct that the macro-level management happens far away from the noise.
Okay, good.
For that, the datasheet relies heavily on a protocol called Redfish, alongside integration with SuperCloud Composer.
Yeah, Redfish is plastered all over this catalog. Almost every single model supports it. For a listener who understands networking but maybe hasn't managed bare metal hardware, how does Redfish change the game here?
Well, Redfish essentially revolutionized data center infrastructure management, or DCIM.
Okay.
Historically, the physical layer of a data center was deeply fragmented. You had server motherboards from one vendor, power supplies from another vendor, and cooling systems from a third.
Sounds like a mess.
It was. They all communicated using proprietary legacy protocols. Trying to get a holistic view of the data center's health was just a nightmare of incompatible translation layers.
It was like having a team where everyone speaks a different language and you need 5 different interpreters just to know if the building is on fire.
That's a perfect analogy. Redfish acts as the universal translator. It is an open industry standard that essentially turns dumb physical hardware into intelligent devices that can be managed via standard RESTful APIs.
Right.
It uses HTTPS and JSON payloads, the exact same ubiquitous web technologies used to manage cloud software.
So a software engineer can send a standard digital request to a massive liquid-filled mechanical door, and the door responds with a structured data payload detailing its exact thermal state.
Exactly. And more importantly, it allows the overarching management software like Supermicro's SuperCloud Composer to automate the physical world.
Okay, how so?
Let's say the orchestrator software knows it is about to spin up a massive, intensive AI training workload on a specific rack. Because the door speaks Redfish, the software can preemptively send a command to the RDHX to increase liquid flow rate and fan RPM 30 seconds before the GPUs actually spike and generate the heat.
Wow. It transitions the cooling from a reactive posture, waiting for the air to get hot, to a predictive posture.
Precisely.
The digital software is directly choreographing the physical plumbing.
It creates a unified nervous system where the compute load and the physical cooling infrastructure operate as a single breathing organism.
That is just so cool. And that perfectly sets the stage for the hardware catalog itself. We've established the governing philosophy, the aerodynamic physics, the thermodynamics of condensation, and the digital nervous system.
We covered the groundwork.
Now, I want to dig into the actual physical units detailed in the datasheet. Because Supermicro didn't just build one door, they built an entire spectrum tailored to very specific engineering constraints.
Yeah, the catalog is divided by thermal capacity and physical architecture. And the most extreme engineering happens at the absolute top of the spectrum, the heavyweights.
These are the units engineered for the absolute bleeding edge of hyperdense AI, the 100 kilowatt to 120 kilowatt class.
The big ones.
Looking at the specs, the flagship is the SRK92RDCC. It offers up to 120 kilowatts of heat removal. It operates on standard AC power, utilizes a 7-fan array, and pulls a maximum of 3.85 kilowatts of power just to run its own mechanics.
Yep.
But the number that jumps off the page for me is the physical mass. It weighs 156 kilograms.
That is roughly 345 pounds.
345 pounds of steel, copper coils, and industrial motors, designed to hang entirely off the rear frame of a server rack. And that weight is without the liquid coolant bumped into it.
The structural implications of that are profound. You cannot just bolt 345 pounds to the back of a standard metal cabinet without fundamentally altering its center of gravity.
I would imagine it would just tip backward.
It could. Data center racks are heavily loaded with servers in the front, but hanging this massive cantilevered weight off the rear requires specific structural reinforcement. Furthermore, it impacts the floor loading of the entire facility.
Oh, the floor itself.
Yeah, modern data centers often utilize raised floor tiles to allow for underfloor cabling or legacy cooling.
And those individual tiles have strict point load limits, right?
Exactly. If you add nearly 400 pounds of operational weight to the rear casters of a rack, you are pushing the structural engineering of the floor itself to its absolute limits.
It is a massive physical footprint, but the SRK92 isn't the only giant. There is a slight step down in capacity, the SRK82RDCC.
Oh.
It handles 100 kilowatts, uses 6 fans, pulls 3.3 kilowatts of power, and weighs 146 kilograms.
And both of those models, the 92 and the 82, share a distinct architectural advantage according to the sheet. They are cross-compatible with multiple rack standards, MGX, EIA, and ORV3.
Which provides immense flexibility for a data center operator, I assume.
Huge flexibility. EIA is your traditional, decades-old 19-inch rack standard. ORV3 is the Open Rack version 3, driven heavily by the Open Compute project for hyperscalers.
Right.
By designing a door that can adapt to all three, operators don't have to rip out and replace their actual metal framing infrastructure just to upgrade their cooling.
But flexibility isn't always the goal, and this is where the datasheet presents a really fascinating engineering puzzle.
Oh, I know the one you mean.
Yeah, there's a third heavyweight model in the 100 kilowatt class. The LCS SRDR 1048000001. We'll just call it the LCS 100 for sanity's sake.
A wise choice.
So the LCS 100 neutralizes exactly 100 kilowatts of heat. Just like the SRK 82, they both run on AC power. But the physical topologies are wildly different.
Entirely.
The SRK 82 achieves its 100 kilowatt cooling using 6 fans and a maximum power draw of 3.3 kilowatts. The LCS 100, on the other hand, utilizes a massive 12-fan array. It draws 5 kilowatts of maximum power, and it weighs even more, hitting 160 kilograms.
This is the perfect example of how specific physical constraints force radical changes in thermodynamic engineering.
Because on paper, it makes absolutely no sense to buy the 12-fan model. It consumes significantly more electricity to achieve the exact same thermal neutralization. Why burn 5 kilowatts of power when you could do the same job with 3.3? It breaks the rule of efficiency.
It does look strange. But to solve the puzzle, you have to look at two specific parameters in the datasheet: rack compatibility and physical depth.
Okay.
The 6-fan SRK82 fits multiple racks and has a physical depth ranging from 400 to 470 millimeters. It protrudes nearly half a meter into the aisle.
Okay, so it's incredibly thick.
Now look at the depth of the 12-fan LCS 100.
Okay, let me see. It says the depth is only 280 millimeters without an extender. It's barely over half the thickness of the other door, and it is strictly limited to EIA racks.
Therein lies the engineering compromise. In many legacy data centers, aisle space is a premium commodity.
Oh, because the rows are close together.
Exactly. If the physical walkways between the rows of racks are too narrow, a facility simply cannot deploy a door that sticks out 470 millimeters. It would block technician access or violate fire codes. They mandate a low-profile solution.
But compressing a 100 kilowatt liquid radiator into a 280 millimeter frame changes the aerodynamics, doesn't it? If the door is that much thinner, you physically cannot fit large diameter fan blades inside it.
You can't. And this comes down to the basic physics of airflow. The volume of air a fan can move the cubic feet per minute, or CFM, is heavily dictated by the swept area of the fan blades.
Right.
If you are forced to use smaller diameter fans to fit a thin door profile, you drastically reduce the swept area.
So to move the massive volume of air required to pull 100 kilowatts of heat out of a server, a small fan has to spin exponentially faster than a large fan.
Exponentially faster, and rotational velocity requires power. To match the volumetric airflow of 6 large, slow-spinning fans, the engineers had to pack 12 small fans into the door and drive those motors at incredibly high RPMs.
Wow.
That massive jump in rotational friction and motor strain is what drives the power consumption up from 3.3 kilowatts to 5 kilowatts.
It is a pure trade-off. The operator is basically trading electrical efficiency and acoustic noise, because I imagine 12 small fans screaming at high RPM are going to generate a much higher-pitched, aggressive sound profile.
It's deafening.
Right, so they trade that for physical real estate. If the aisle is too narrow, the operator just accepts the higher power bill as the cost of doing business.
It highlights that there is no singular best design in infrastructure. Every single data center has a unique physical geometry, and the hardware must conform to that geometry.
Which transitions us perfectly into the next tier of the catalog, because not every data center is pushing the limits of known thermodynamics with 120 kilowatt clusters.
No, most aren't.
Many enterprise workloads, heavy databases, virtualization, standard cloud hosting, they run incredibly hot, but they operate in what I'd call the mid-tier zone.
The 50 kilowatt to 80 kilowatt range. These are the absolute workhorses of the modern enterprise.
Leading this tier is the SRK 52RDCC. It offers 80 kilowatt of capacity, operates on AC power with 5 fans, pulls a highly efficient 2.1 kilowatt and weighs 136 kilos. But the catalog gets deeply highly specialized when we look at the 50 kilowatt capacity limits.
It really does.
Supermicro offers 3 totally distinct models that all max out at exactly 50 kilowatts of cooling.
And once again, they arrive at that 50 kilowatt threshold using vastly different combinations of power supply, fan topology, and rack architecture.
Let's lay them out. First, we have the SRK 42RDCC. It is highly versatile, accepting both DC and AC power. It utilizes just 4 fans, pulls a mere 1.7 kilowatts of power, weighs 114 kilograms, and is 375 millimeters deep. It seems like the standard highly efficient baseline.
It is. It's the versatile all-rounder.
But then we have the LCS SCDU050AR001. We'll call the LCS 050.
Good call.
This model also cools 50 kilowatts, but it is strictly limited to DC power and strictly limited to MGX racks. Furthermore, to achieve that same 50 kilowatt of cooling, it requires 10 fans, draws nearly double the power at 3.3 kilowatts, and is shallower at 310 millimeters deep.
So we are seeing the exact same physical constraints play out here as we saw in the heavyweights.
The depth issue again.
Exactly. The LCS 050 is a shallower door designed specifically for custom MGX rack architectures, which forces the use of a larger array of smaller, power-hungry fans. But the really critical detail here is the power supply. The LCS 050 is strictly direct current.
We touched on DC power earlier when discussing the bus bars, but why would a data center operator purposefully limit themselves to a DC-only door? Why not maintain the flexibility of AC?
It comes down to macro-level power efficiency. At a foundational level, computer components, CPUs, GPUs, memory, they all operate on direct current.
Right.
But the grid delivers power to the building as alternating current.
So somewhere in the chain, the AC has to be converted to DC. In a standard setup, that happens at the individual server level, doesn't it? Every single server chassis has its own power supply unit doing the rectification.
Yes, and that conversion process is never 100% efficient.
Yeah.
The physical byproduct of rectifying AC to DC is heat.
Ah, of course.
So in a highly dense rack, having 40 individual power supplies all generating conversion heat inside the chassis exacerbates the thermal problem before the processors even start calculating.
That is incredibly counterproductive. You're generating heat just to turn on the machine that generates heat.
Which is why architectures like MGX, driven by hyperscalers, often move the rectification out of the server entirely. They convert massive amounts of AC to DC at a centralized point in the rack, and then run pure DC power straight down that thick copper bus bar we discussed earlier.
Right, the electrified spine.
By doing this, they eliminate 40 points of heat generation inside the rack.
And because the entire rack is now natively operating on DC power, the RDHX door is engineered to clip straight into that DC busbar, avoiding its own localized conversion losses.
Exactly.
It's a holistic commitment to a specific power topology to scrape back every fraction of a % of thermal efficiency.
It is highly specialized engineering. And for operators who don't have that DC infrastructure, Supermicro provides the third 50 kilowatt model, which is exclusively AC powered, uses 6 fans, and is designed strictly for standard EIA racks.
They are essentially creating a matrix of solutions covering every possible permutation of power delivery and physical rack size.
They leave no architectural stone unturned.
But all of these models, from the 120 kilowatt behemoths to the 50 kilowatt workhorses, assume one fundamental reality.
What's that?
The data center actually has the physical plumbing to deliver chilled liquid to the rack in the first place. What happens when that assumption is false?
Well, that is the reality for a massive percentage of the industry. You cannot simply pause a live, revenue-generating data center, tear up the raised floor, and install miles of pressurized water pipes overnight.
No, I imagine not.
The transition to liquid cooling takes years of capital expenditure.
Which brings us to what I think is the most fascinating section of this datasheet, the lightweight division. The solutions designed for lower thermal thresholds and transitionary environments.
We are looking at the 20 kilowatt class. It's a stark reminder of how fast technology moves, honestly. A decade ago, a rack generating 20 kilowatts was considered a high-density, blisteringly hot deployment.
And today?
Today, it's the absolute floor of the RDHX catalog.
Wow. For the fully plumbed setups, there are 2 standard liquid-cooled 20 kilowatt models. A DC-powered 8-fan unit for MGX, and an AC-powered 5-fan unit for standard EIA racks. They both weigh around 110 to 120 kilograms.
Right.
They are essentially scaled-down iterations of the mid-tier doors, providing localized liquid cooling for less intense thermal loads.
But the truly disruptive piece of engineering in this catalog is the final entry.
The SRK-10 RDCC. I stared at the specifications for this unit for 10 minutes trying to understand what it was doing.
It's a weird one.
It claims up to 20 kilowatts of cooling capacity. It can run on DC or AC power, but the physical metrics are shocking. It only has 3 fans. It pulls a microscopic zero point 0.8 kilowatts of maximum power, and most crucially, it only weighs 64 kilograms.
64 kilograms is roughly 140 pounds. That is a massive anomaly compared to the 300-plus pound liquid doors,
And the datasheet includes a parenthetical note next to the model name that explains the weight discrepancy entirely. It reads, fan door only.
which means it completely lacks the internal plumbing.
No copper coils, no chilled liquid loop, no smart anti-condensation system. It is fundamentally a metal frame with 3 industrial fans bolted to it.
That's moving air.
How can a door with 0 thermodynamic heat exchange claim to provide 20 kilowatts of cooling capacity? It violates everything we've discussed about intercepting residual heat with liquid.
Because it isn't neutralizing the heat. It is radically altering the aerodynamic pressure of the rack to maximize ambient air cooling. It is a piece of bridge technology designed for legacy environments.
Okay, let's explore the physics of a legacy 20 kilowatt rack then. You have a standard metal cabinet filled with densely packed 1U servers. Inside those servers are tiny 40-millimeter fans screaming at 20,000 RPM, desperately trying to push ambient room air across the heat sinks.
And as that air moves through the server, it hits intense physical resistance. Network cables, power supplies, the dense layout of the motherboard itself. By the time the hot air reaches the rear exhaust panel of the server, it has lost most of its kinetic energy.
It creates a traffic jam. The hot air wants to exit, but there isn't enough pressure pushing it out into the room.
We call that back pressure. The heat pools at the rear of the rack, creating a localized thermal dam. The servers start choking on their own residual heat because they simply cannot exhaust it fast enough.
And this is where the SRK 10R DCC fan door fundamentally changes the equation. By sealing the rear of the rack with this door, those 3 large fans create a massive zone of negative pressure, a vacuum, right at the exhaust point of the servers.
It acts as an airflow accelerator. The door violently sucks the hot air out of the congested server chassis, breaking the thermal dam, and blasts it out into the room's main AC return path.
I see.
It dramatically lowers the static pressure barrier that the internal server fans were struggling against.
It basically turbocharges the exhaust velocity. It doesn't chill the air, but it moves it so fast that 20 kilowatts of heat can't pool and cause a meltdown.
Exactly. But the obvious question is, why buy an entire smart door to do this? Why not just buy more powerful fans for the servers themselves?
Because of the digital intelligence we spent so much time analyzing earlier, if you look at the protocol supported by this 64-kilo fan door, it features the exact same WebUI, SNMP support, and crucially, Redfish integration as the 120-kilowatt behemoth.
It is a Trojan horse for modern data center management.
A facility operator might have a massive room filled with quote-unquote dumb legacy racks that have no native way to communicate their aerodynamic state.
Right.
By attaching these relatively inexpensive lightweight fan doors, which pull less than 1 kilowatt of power, the operator instantly brings those legacy racks into the Super Cloud Composer ecosystem.
It bridges the physical divide perfectly. The operator can now use their centralized dashboard to dynamically automate the airflow of their 10-year-old storage arrays right alongside their brand-new liquid-cooled AI clusters.
That's brilliant.
It provides visibility and control over environments that were previously completely dark to the orchestrator software.
It acknowledges the economic reality of infrastructure. You don't get to just start from scratch. You have to iterate. And the SRK 10R DCC is the perfect iterative stepping stone.
It allows a facility to stabilize their thermal thresholds and digitize their management today, buying them the necessary time to architect the liquid cooling plumbing they will absolutely need tomorrow.
Which really brings us back to where we started, the physical reality of the cloud. Over the last hour or so, we've taken a dense engineering spec sheet and used it to map the invisible architecture of the internet.
It's been quite a journey. We examined the failure of traditional room-scale air conditioning in the face of hyperdense AI computing.
Yeah.
We explored the thermodynamic philosophy of intercepting residual heat right at the boundary layer with massive liquid radiators.
We analyzed the fluid dynamics of N+1 redundant fan arrays and how millisecond digital responses create mechanical fault tolerance. We looked at the terrifying psychrometrics of dew points in a hot aisle and how modulating valves prevent a multi-million-dollar rainstorm.
We decoded the structural constraints that force engineers to choose between high-efficiency fans and narrow aisle deployments, and why the rack-level power topography dictates the internal components of the door.
And we saw how the Redfish protocol weaves these massive industrial machines into a single automated digital nervous system. It is just a stunning symphony of physical and software engineering, all dedicated to one singular goal.
removing thermal energy from a microchip as fast as the laws of physics will allow.
It reveals the intense, staggering scale of the heavy industry required to power our digital lives.
Right.
Every time we interact with a generative AI or query a massive database, we are relying on these mechanical leviathans to hold back the heat.
It fundamentally changes how you perceive the technology in your pocket. The digital world is dictated entirely by the survival of the physical infrastructure.
And looking at the trajectory mapped out in this datasheet, it leaves us with a profound engineering dilemma for the next decade. We have already had to abandon cooling the room, moving the chilling apparatus directly to the rear door of the rack to capture the residual heat.
Yeah.
But processor architectures are getting exponentially hotter with every iteration. The thermal density is compounding.
It really begs a massive question. What happens when the 120 kilowatt limit is breached?
Yeah.
And even a liquid door is just too far away to stop the meltdown? Will the next era of data center engineering be forced to abandon airflow entirely, bypassing the chassis and pumping chilled liquid directly into the microscopic architecture of the silicon chips themselves?
Now that is a thought to leave you with. Until next time.